let's go.
Okay, yeah. Okay, hello everyone. My name is Yinan Zhao. I'm a postdoc in University of Geneva, working with Dr. Xavier Dumusc on modeling and mitigating stellar activity in the RV dataset. So today I will talk about our new code, SOAP GPU, to model the stellar activity in the spectral domain. So I think, yeah, this is the first time I run the tutorial. So basically, I'm not sure how it will go. And just basically, I will just spend like 35 minutes on the slides and maybe 25 minutes on the code. So basically, since most of the code will be run on GPU, so basically, I will just demonstrate how the code will run on my side. So basically, people willing to use this code or maybe want to develop their own version on top of that, you can go ahead and direct message me in Slack or maybe just send me an email. Okay. Okay, so basically first thing why I start this tutorial is that I need to run the SOAP tool first, because I think it takes a lot of time to finish. And we really want to compare how the performance of different algorithm. So basically here, yeah, I'll just run the SOAP tool first.
Yinan, can you maybe make the terminal, like the text in the terminal a little bit bigger?
Maybe also you can do focus on content. So the...
Oh yeah, it's really have the
Yeah, this is
yeah, I think that's better. Yeah, I was thinking even if you're on your own.
Yinan, normally if you do like a command plus, it should. Yeah, good.
Oh.
Awesome. Thank you.
Yeah, so basically everyone can see the slides, right?
Yes.
Mm-hmm.
Okay. Okay, so so basically we develop a code called the SOAP GPU. So basically, I think most of people know what is SOAP, but here I want to introduce you guys about the GPU and the GPU computing. So here it's a comparison of the CPU and GPU I downloaded from the NVIDIA website. So in principle, we know that for the CPU, it only have maybe like 4 or 8 cores. Maybe each core have 2 threads, and it can, for each thread in the CPU, it can like do some like complicated jobs. But I think for the GPU, it has many core, many threads. I think it's up to like 2 to the 31 minus 1, something like that, numbers of thread. And each thread can do like a simple operations like a plus or minus. So here is a very basic comparison of CPU and GPU. So basically, imagine that if we want to deliver a package as soon as possible, and so basically CPU is just a very spot car, you probably go ahead and use the spot car to deliver your package. But what if you have like many package and you just want to deliver it at a reasonable time? So maybe the GPU is just a team of scooters. So basically, instead of like deliver it one by one, you want to use your scooter, although individually it will slow, but it can deliver the package simultaneously. So that's how the GPU works. So basically, although each thread performance is lower than the CPU, but I think the most advantage is it has a lot of computational thread. So compared with CPU, the GPU can solve the problems by breaking them into different tasks and processing them simultaneously. So basically, the GPU has a great advantage in solving problems involving like a matrix or vectors, such as like convolutions, data interpolations, and data filtering. I think for the convolution, I think most people will get familiar with the neural network. I think the first neural network algorithm is developed in 1981 or 1982. But I think most people know after like 2010 or maybe 2012. I think that's where the NVIDIA has their graphic card and really can boost this convolution and make the algorithm faster enough to get a better performance. So in order to use the GPU to solve your problem, you need to like pixelate your problems. You just break your problems into different pieces and solve them like simultaneously. Okay, next one is that how to use the GPU. So here in our soap code, we use a package called CUDA. CUDA is like a compiler or the toolkit and a library for programming, for GPU programming dedicated to NVIDIA graphical card. It can allows you just using the C and the C++ programming language to call the GPU to run your code. So basically, here are some like keywords when you're using the GPU. The first one is the building block of the GPU. It's called a thread. The thread is like a single computational unit in GPU. So basically, a group of a thread can be formed called block. So basically, all the threads in the same block, they can communicate with each other and share the memory with each other. So that's the reason it can boost the computation of your algorithm. So the next level is a grid. So a grid is a group of just a group of blocks. So here it is the basic structure of the GPU. So basically the building block is thread, and the upper level is block, and the and then is it's called grid. Okay, so here is the typical syntax when you run your function with CUDA or GPU. So basically, you first need to define your functions, and you need to define your variables. And besides that, the key part is that you need to define how many blocks and how many threads you want to use to parallelize our algorithm in GPU. Okay. So next part is that I will introduce you guys the basic architecture of our new code called the SOAP GPU. I think it's a little bit similar structure of the SOAP, but I revised a little bit. So the first thing when you run the SOAP GPU, so basically it will generate the integrated quiet sense spectrum. So first of all, so basically we use so basically we need a quiet sense spectrum. It can be either like observed quiet sense spectrum. It also can be like a simulate or a spectrum from the hydrodynamic simulations, and we call it a seed spectrum. And so basically, when you read the spectrum, it first will be allocated in your CPU. The key part is that you need to, when you use GPU, you need to copy the data from your CPU memory to the GPU memory, and then you can do your performance. So next part is that we need to initialize a stellar disk. The stellar disk is defined by the certain resolution here. For example, here I use a resolution 300 by 300, and it also need to be initialized by some physical parameters like the inclination angles, the effective temperature of your star, and the period of the star, and the limb darkening parameters. And after you initialize with your disk, it can generate this kind of like a velocity disk and also the light distribution disk. And so basically, next step is that we need to put the seed spectra into each pixel of the stellar disk, and for each pixel, we take the light ratio or light in that pixel, and also the velocity in that pixel, and inject it to the seed spectrum. For example, we need to, for certain pixel, we need to take the velocity component and inject it to the quiet sense spectrum, which means that we need to shift the quiet spectrum and reinterpolate the spectra into the original wavelength space or the velocity space. And so basically for each pixel, we do this kind of like injection. We inject the velocity, and then for this part, the interpolation part, we just employ the GPU to do the fast interpolations. once you have your spectra at each pixel interpolated back to the original wavelength domain, you can just do the integration over the entire disk by summing all the spectrum up over the entire disk to get the integrated quiescent spectrum. So the next part is that we need to inject the active region spectra again. So basically, for the active region, we need to see the spectrum. It can either be like a real spot observation from the real observations, or it can be like a hydrodynamic simulation of different temperature of the spectrum. So so basically, when we inject the spot and the facula, we need some like physical parameters to initialize their locations. For example, we need to know the numbers of the active region we want to simulate. And also at each time step, we need to know the geometry coordinate, like the latitude and longitude for each facula or spot. Or if you want your spot or facula evolving with time, you also need to input the evolutionary parameters like a decay rate or maybe increasing rate. So after you have those parameters, so basically we launch like a rotational matrix to compute the active region location at each phase at the stellar disk. So next one is that within the active region in the stellar disk, we need to calculate the differences between the quiescent spectrum we used before and the spot spectrum we use here. We calculate these differences, and in the active region pixel, we still need to inject the velocity and the light distribution into these differences. And here we again using the GPU to do this kind of like a faster interpolations, and we integrated over the active regions to get the integrated differences spectrum. So the next step is that from the previous step, we get the integrated quiescent spectrum, and we get the integrated difference spectrum at each phase. So basically, we use the integrated quiescent spectrum to subtract the differences integrated spectrum at each phase. So basically, we can get the final active spectrum with activity at each phase. So since most of the simulation we run here is the high resolution simulation from the FTS spectrum. So basically, in order to compare with the SOAP, in order to compare with the HARPS observations, we need to lower the spectral resolution to match the HARPS observations. So here we're still using the GPU to do the convolution to lower the resolution of the high resolution spectrum we simulated. And also after we get the lower resolution spectrum, we also use the GPU to fast calculate the CCF of those spectrum, because in principle the CCF is just the correlation of the template and your spectrum. So basically we can also using this to do the faster cross correlation with the GPU. So basically after we get the CCFs and the activity spectrum, we can copy it back to the CPU and save it in our computer disk. And we also need using the minimization algorithm to calculate the final RV products, like the RV values and the CCF contrast and the bisector span with the CPU. So basically, that's how the SOAP GPU works. So here I will show you the computational efficiency comparison of SOAP2 and SOAP. So the figure on the left is the SOAP GPU, the speed comparison of those two algorithms. So basically, in order to check the speed, we just calculate the integrated quiescent spectrum. Because in order to calculate the quiescent spectrum, we really needed to integrate the entire stellar disk, which is like 300 by 300 typically. So for the lower if the disk resolution is lower, for example, like if the disk resolution is like below like 10 by 10, I think the SOP2 is faster. The reason behind that is that I think as I mentioned before, the bottleneck of the GPU algorithm is the communication of the CPU and GPU. You need to copy it back and forth between those two machines. So basically, it will drag down the computational efficiency a little bit. But after it reach like a higher resolution, so basically it really gain a lot of like computational speed from the GPU computation. As you can see, for example, if the disk resolution reach like 300 by 300, the speed is improved by a factor of 100 just by calculating the integrated quiescent spectrum. Okay, so next one is that we calculate the performance. We compare the performance of one stellar activity. So here the figure on the right is that we use both SOP2 and SOP GPU to simulate a same spot configuration, which is that we simulate a single spot with 1% of the stellar disk, and the disk is a resolution 300 by 300, and the longitude is like 118 degree. Longitude is like 13 degrees. So basically, we just simulate one rotational phase. So basically, compare with the SOP2, which use around like a half an hour. Here we only use like a half minute to simulate 100 spectrum with a new NVIDIA graphic card. So basically, the computational speed is improved by a factor of like 16. Okay, so here I can show you how the performance of the code currently. Let's see. Okay, yeah. So basically, we just let the SOP2 run, and we can run the code here. Okay, I will briefly. So basically, in order to run the SOP code,
would it be possible to make it bigger, your terminal?
Yeah, I already did. I'm not sure if
That's getting better, yeah.
Yeah, it's better.
Okay.
Yeah.
Okay, so let me first run. So basically, in order to install the SOP2, you just using the bash to install it. So basically, it will compile all the corresponding library of the SOP GPU. Okay. Okay, next we can run the code. So the first step is calculating the integrated quiescent spectrum. Yeah, it takes 8 seconds, and then it will calculate the stellar, the different spectrum at each phase, and then to subtract and lower the resolution. Yeah, it takes 28 seconds. So next, so here it will use the CPU to calculate the RV data point for each spectrum. And we can see that, yeah, SOP2 is still running the differences spectrum.
No, it's like a race.
Sorry?
It's like a race.
It's like a turtle and a rabbit. Like.
Oh, watch out, I think the turtle wins that one, right?
Yeah, but I think in this case it will be the... And so here it computes the effect from the flux, the effect from the convective blueshift, the total of it. So then as output, you can also have like investigate which contribution those two different components have.
Yep, it takes less than 2 minutes to finish the entire run. Okay, so I will show you the results. I need to download the data.
So Yinan, while we're waiting, the original code, so it's still running?
Yeah, I think it's still running the generation. Yeah. Yeah. And then
is the code running the original SOAP too?
Yeah, we had a version that where we could inject spectrum and not CCR.
Okay.
And but it was taking forever.
That's why you switched to the GPU.
Yeah. That's before it was nonsense, like
to
use it or just to like one spot, one rotational phase, and that was the most we could do in 1 hour or something like that.
Oh wow!
So then when we were starting to put more spots, it
was
impossible. Let me see. Right. Yeah, we got the, and then we launch the.
Nice.
Okay, so basically, I mean, I think since SOAP2 is still running, so basically I already got the result from the SOAP2 from the previous calculation. So basically I can just show you the direct comparison between different algorithm, which is in agreement with each other. And yeah, all right, I already downloaded the simulated data from the server. Let me see. Oh, here, which is called this one, spectrum. And so basically we can visualize the spectrum a little bit, see how the spectrum looks like.
Can you make it bigger? Sorry.
Yeah, okay. Okay. Data. Oh. Okay. The wavelength data. Yeah, usually we have like a 100 and plus 1. The last plus 1 is the quiet sense spectrum, I see. So, yeah. Okay, so basically we can really examine some of the line. For example, we can maybe just copy from here. No. Example reasons. And yeah. Back cube. And okay, you can really see some of the line region, for example, here. Yeah, but still we cannot see the how the line performs with time. So basically, the y-axis is the time domain, and the x is the wavelength domain. So basically, we will zoom in, maybe for example, from like a 420 to 480.
So basically, Yinan, just so what you were showing in this plot was like the spectral residuals.
Yeah. You will use the first one to subtract the rest.
Okay, yeah. So we see basically the difference between the spectra as a function of time at the level of spectral length in this case.
Yeah, and we can so really here we can use like a PCA to quickly demonstrate how each component perform. Like okay, so basically here we use 5 PCA. And so basically we can visualize the first component, actually, which is capture the light evolution of these simulations. But you can see at the beginning it become stronger, and it become lower, and it will come back. So just as the light curve profile of your simulated data. And if we change it to the second component, which will be the velocity component here. Yeah, you might see. So really think at the beginning it will shift the peak shift here, and as the times involved it will become 0 and go back to the opposite. Yeah.
Wait, sorry, can you walk through this plot one more time? What's on the x-axis?
So the x-axis is the wavelength, but I just zoom in, so basically just in terms of the pixel.
Gotcha, okay.
Yeah. And the y is the time slide.
Time standstill. Okay, thank you.
Yeah, like I think the first 1/3 and the last
there's like bands at the top.
The first and the
bottom.
last, this is where basically there is no spots, it's behind the star.
Okay, thank you.
And then the spots pass by, and you see like this Doppler shift, and then this changing depth of the line as well.
Okay. Thanks.
Okay, yeah. So next we can continue, and we can continue to the activity region properties. Like here, I will introduce you how the subcode will handle the different spot or facular properties like the size evolutions and the numbers of the spot evolutions and so on. Okay, so basically here is a figure of a SOAP GPU simulation of different active region evolutionary curve. So basically, I think of all the simulation here is initialized with the spot, with a single spot, and with a latitude 13 degree and longitude of 118 degrees. And for the fourth column, I think the figure on the top is the evolutionary curve. As you can see, it's like a symmetrical Gaussian, which means which can model the increase phase and the decrease phase of one spot. And the maximum of the spot is just 1% of the entire disk. And as you can see in the second figure of the light curve, you can see the gradients of this light curve. It's hard to say, but you can get a little bit sense about that. Really, the gradient increase as the spot size increase and decrease as the spot decrease. And the second column is the decay curve for the spot. The maximum size of is still 1% of the entire disk, and it starts to decay over the entire phase. And you can see the light curve, the gradient of light curve decrease also with time. And the last column is the growth evolution for the spot, which is beginning at 1% of the stellar disk, and the light curve gradient light curve increase with time. So the next step is that so basically we can really simulate different complex configuration of the stellar activity regions. For example, here I simulate a spot with 1% of the stellar disk first, and then surrounded the spot will be surrounded by a facula at the same place, but with the larger area of like a 3%, no, not 3%, 9% of the stellar disk, and it will evolve with time. So really, as you can see, for example, in the flux effect, you can really see the flux effect of this combined configuration is just a kind of like linear combination of the individual flux effect and the facula effect. So basically, as I showed you before, we can simulate the spot size evolution and also the complicated spot configurations. And here I just want to show you we can simulate the stellar activity with the numbers of the spot evolution. So basically, the figure here is the spot number observation from the SDC from the real observations. So basically, we use this as the number of the spots we simulate, and we also assume that the ratio of spot and facula to a certain values. And so basically, for this figure, we also implement the butterfly diagram and also the active longitude region, or when the spot rotated with the stellar disk. And so the figure on the right is I simulated the 4 years of data array of this kind of like configurations with different inclination angles. As you can see, when the inclination angle is larger, which means that the active longitude is in the equator of the disk, the signal is much more stronger as the longitude, as the inclination becomes smaller, which means that the active longitude shifted to the higher longitude, which means that the spot activity region activity effect becomes weaker. As you can see in the red curve of the periodic graph, you can see the period really diminished with the stellar with the inclination angles. Okay, so let me see. Yeah, it's finished. Oh, this time it's faster. It's like not half an hour. Yeah. 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 So next thing is that since we can simulate the stellar activity with the numbers of spot evolutionary curve from the real observation, the next step is that can we just directly simulate the stellar activity from the SDO image? The answer is yes. So basically here we're just using the SDO data at each time step, and so basically here the spot and the faculty location are extracted by our PhD student Khaled. So basically here, after we get the location of the stellar active region at the stellar disk, we can feed into the code and really to simulate how the RV and the spectrum perform with the SDO data. And so basically here we have the simulated RV data from based on the SDO image. And we also compare it with the hard solar spectrum data. But as you can see, when the spot configuration is correct, so basically we can really model the real RV spectrum from the real observation.
It almost looks like there's a time lag. Right?
Yeah. I think the time lag will be introduced by Khaled in his talks. Yeah.
Interesting.
Yeah, so we have a time lag indeed. We don't really understand where it's coming from. At one point, we're saying this could be the way like we are looking from Earth and from the satellites. If it could be this, it doesn't seem, because here we have a time lag of 2 days or so.
Okay.
But yeah, for the moment, we don't fully understand what is happening at this level. But it models it quite well.
Yeah.
Except
No,
this
the
time
shape
lag.
is
Yeah,
totally
except,
right.
except this like 2-3 days, indeed.
So does that cancel out the temporal offset thing, the shift?
Sorry?
Does that cancel out the temporal offset, the shift? Time like that analyst was talking about yesterday. Does that cancel out that effect?
It's like the same magnitude as it,
Okay.
but not sure it's in the same direction as the indicators. But it could be worth checking.
Okay. Yeah. So next step is we investigate the stellar activity by their spectral properties. The first one is that we investigate the geometric effect of how the stellar activity will have impact on our RV. So I think before the simulation, we just simulated the stellar activity, the entire spectrum, 4,000 to 6,000 astrons. But here we just using the blue part to see how the spectrum perform. I think the corresponding array are shown below. So basically compare with, so in the flux effect of the different color, as you can see, the flux effect of the red part of the spectrum is less stronger than the blue part. I think which makes sense, because when you calculate the contrast of the spot, contrast of the spot and the stellar disk, for the blue part of the contrast is larger than red. So basically it will give the flux effect stronger in the blue end. So really for the inhibition of the convective blueshift, I think most of people know that this effect will never go below 0. But for this kind of simulation, as you can see, for the red part, it's really, I think half of the data go below 0. I think the most possible reason is that the imperfect normalization of the red part, because I think the red part of the spectrum, it has a lot of absorption lines. Basically, it's very hard to model the data. So basically, I think the imperfect normalization of the data will introduce a little bit more flux effect into these simulations. So, but I think for the blue part, which is normalized very well, you can see all the inhibition of all this convective blueshift effect is above 0. Okay. So next step is that we investigate the convective blueshift shift as a function of mu angles, because due to the recent paper, so basically in this paper they studied the white sun spectrum at different mu angles, and they found out that the bisector of the white sun spectrum at different mu angle perform differently. So basically here we will also implement this effect as a function of the mu angle in our simulations. So first of all, we measure all the bisector of those lines at different mu angles as shown here. I think most of the line they have kind of like a similar trend, which is that at the mu angle, smaller mu angles, it has a large Doppler effect, and as the mu angle go bigger, and I think the Doppler the bisector go to the blue part, and around like maybe mu equals 0.85 or maybe 0.9 to go back again. I think most of the line follow this same trend, and if we plot the line in the same mu angle, so basically we can get for each mu angle, so we have like a bunch of lines of bisectors. So basically here we just model those bisector with a polynomial at different mu angles. So basically we can derive a model based on the observation of the bisector as a function of the mu angles. So next step is that we need to inject this derived bisector into our seed spectrum, and we can just recalculate all the effect. So before we inject it to the to our spectrum. So first of all, we need to remove the current bisector of the spectrum. So the key part is that when we measure the bisector, we are really measure the bisector from the CCF. So basically, the CCF, I think most of the time the CCF will not reach like below 0.4, maybe 0.5. So basically, with the bisector measured from the CCF, we can only correct for the shallow lines, but for the deep lines, we just here use some strong iron line to model the deep line bisector, and after we derive the bisector, we can use this polynomial to model the entire bisector of the spectrum. And so basically, after we derive this, we can using this curve to correct for the current bisector in the spectrum we use. So after we do the corrections, we get the clean spectrum, seed spectrum. The next part is that we need to inject the mu-dependent spectrum into our clean spectrum. So for the quiet sun spectrum, we only need to inject this kind of like a mu-dependent bisector. So after we inject it, instead of previously we use one spectrum to model the stellar disk. Here we use, for example, here we use 10 spectrum to model the quiet sun disk, because I think at each mu angles we use different spectrum with different bisectors. And for the spot spectrum, we just injected the same bisector as a function of the mu angles, but we also need to add this spot quite difference bisector to calculate the shift of the active region. So basically, after we inject both, we can get the spectral cube for the spot seed spectrum. So basically here, before we know that we only injected one spectrum, but here we just at each mu angles just using different spectrum generated in the previous step model the data. So I think here I want to show you how this code works. for this part.
I have a question regarding when you inject bisector in the spectrum. You showed that at different mu angles, you only see, you can see that for each line it changes in a different way. So how do you inject bisector in all the lines in spectrum?
I think, okay, so basically I think in their paper, I think they only provided some of the deep lines, and if you plot all the deep line in, for example, in the same mu angle domain, you can see this kind of like a curve. So basically each line is a different line bisector at the same mu angles. So basically we're just using polynomial to fit the entire trend to get the bisector for the entire spectrum.
But you only show like 10 lines here in the plot. So are there?
Yeah. So basically here we only use the strong lines. I think, I think this is like just the first order approximations. I think it maybe not works for the shallow lines, but I think this is the only data available for our simulation right now.
So at first approximation, all the lines have the same bisector, and this is the approximation that we do. That we put the same bisector for all the lines because line depth as the first order is like is similar to depth in the photosphere. So the velocity of convection at each depth is different. But it's true that mainly if you start to take an iron line and then a titanium line, or then they will be from a different depth for the same different physical height in the atmosphere for the same depth, and then it will not. But I don't know, 2,000 or 3,000 of the lines that we have in the spectrum are iron, most of them. So, but it's it's an approximation we are doing for sure.
Use one thing, Yinan, you think you can start to wrap up because we have 7 minutes left.
Okay, I will just show you how the code will run. Maybe show this. So I think maybe it's hard to see. Can you see it clearly or?
Very small.
Okay, then maybe just copy it here.
Okay.
So basically, in order to run the sub GPU, you need to model the config file. So basically, here you need to define the resolution of the disk and the resolution of the active regions and the instrumentation profile here, and the rest is the physical parameters of the stars, like the radii, the radii of the sun, and the ratio of the radii of the sun, and the period and the inclination angles and something like that. And the next one is that you need to define how many active regions you want to use. For example, here, if I only want to use one, I just put here, it will automatically upload the information of the first active region. So if I, for example, put 2 here, it will using the first 2. I think, and next you need to define the longitude and latitude, the size, and also the type. The type 0 means the spot, and the type 1 means specular. And so next step is that we need to define the key parameters here. We need to define how long is the spectrum we use. So here we have like a 500,000 data point, and we need to define how many blocks and the thread we want to use. So basically, you need to remember that the the multiplication of this and this should equal to this one. So basically, you need to really match this with the numbers of blocks times numbers of threads. And this is the step size of your spectral equivalence domain. And yeah, the rest is the input and output directory. And also you need to define your own quite-sense spectral name here, and also the spot spectrum here. And, yeah, that's how the code works. I can show you another one. For example, if you want to run the red part, yeah, so basically if you want to write the red part, for example, if your red part have maybe 200,000 so model modify the numbers of blocks, for example, maybe I put 5 here, and you also need to change the name of the spot and the quadrant spectrum you use. And yeah, I can quickly show you how the code runs.
So a question, Yinan, so you were changing the number of blocks, threads. So this you can change as you want, basically, or like depending on what you will choose, it will affect the performances?
I don't think it will have large effect. I think most of the key part is that the multiplication of these two should equal to your vector set, because I think each thread will take one data point from your spectrum. And another thing is that the numbers of a thread will not be greater than 1024, because that's the maximum thread per blocks you can use. Yeah.
But so because at the thread level, like you have the memory sharing and everything, it's not, the best is not just to put the highest number of thread in terms of optimization?
Yeah. I mean, I think it's all like a tunable parameters, but I don't think, for example, if you use like a 182 instead of 512, it won't like decrease or increase by a factor of 2 or 3. Just maybe like a 0.1 or 0.2 like that.
Okay.
Yeah, so basically this is the maximum blocks you can use and the maximum thread you can use. Yeah, maybe I can run one quick example here. Yeah, maybe the first one. Yeah, still it calculates the quite-sense spectrum. So I show you in the configure file here. So basically all the data product will be saved in this directory. So basically if I go to this directory, I already have some data here. So we will update all the information here. Yep.
So here, what you have all the spectra that are generated and everything?
Yeah, it should start in the resolutions, and it will corresponding save all the spectrum of different effectors into the data cube, so that you can just directly load the entire spectrum at once. And all the array product and the CCF will be saved in this file.
So you mentioned earlier that you could choose, like, for the quiet sun spectrum if you use the observations or a model. Is that something in the configuration file?
Yeah. So yeah, maybe when you leave this slide. Yeah, so basically next few slides I will introduce you guys the different configurations. So basically here we can also use the Phoenix spectrum. So basically
just a bit, I don't know if you all want to stay a bit more longer into tutorial, because we need to be back at 11:30 there. And there is 30 minutes now for coffee. I don't know, you want to stay a bit longer here, listening a bit more, or?
Well, perhaps just wrap up Yinan.
Yeah, I think it's a wrap up just to finish, because I think we all want a small break still before the next discussion.
Yeah, I think as I discussed before, I think for previous simulation we use the real observation, but here we can using the Phoenix spectrum. For example, here I download the Phoenix spectrum at different temperatures and normalize it with the Racine, which is a continuous fitting code developed by Miguel. So after you normalize the data, you can fit into the convective bisector injection code to inject the bisector of different mu angle for the spectrum. And after you do the kind of injection, you will have a data cube of, for example, maybe 500,000 times like 10, because 10 you have 10 bisector at different mu angles. For example, here, if I go to the the simulator is finished. Yeah.
So yeah, basically, if you want to model a star different from the sun with spots that are different temperature, you can download different spectra from Phoenix and then inject them into the code.
Cool. Okay.
So it's not just limited to the sun.
Yeah, so basically you can put the input spectrum here, and yeah, it will automatically grab that into the simulation. Yeah.
This means that it can do near infrared now as well. Because the Phoenix spectra, they go all the way.
So we are able to do near infrared, yeah, indeed. But not telex though, but which is
No, that would be interesting.
Yeah. So So,
do you know how far the Phoenix models go?
Like mid-inf, actually, I'm
10,
looking at
I think they go to 10.
Okay.
But I think with the high resolution, it goes to 5.5 microns.
Okay.
With resolution 500,000. And
yeah, I think the Phoenix go 5.5. Yeah.
5.5. Okay. But thanks a lot, Yinan.
Thank you, Yinan. Let's thank Yinan.
Thanks, everyone.